Let's see.
Okay, so the recording has started. So it's time to start the next talk. So we are very happy to have Professor Takashi Aoki from Kindai University. He will give a talk on the Kummer-WKB dictionary. And as Ines said, this is a discussion session. So if you have a question, or even if it is a live question, you can ask questions even during the talk. And is it okay for Aoki-san? It's okay for people asking you questions during the talk?
Okay. Thank you very much.
Okay.
First of all,
so please start.
I would like to thank the organizers, especially Ms. to give this chance of giving talk. My talk is based on a joint work with Toshinori Takahashi and Mika Tanda. Yesterday, Takei gave a very nice introduction to the exact WKB analysis in his first half part. And latter half part, he applied his the exact WKB analysis to Panve equations. And today, I would like to show you what is obtained if the exact WKB analysis is applied to classically well-known objects, namely hypergeometric functions or equations and its family. Sorry. Okay. You know, the hypergeometric series is given here, where this symbol is the so-called Pochhammer symbol. And we assume ABC are generic complex constants. And also, you know very well about the confluent hypergeometric series of function. These functions satisfy the hypergeometric differential equation or Gauss equation and the Kummer equation respectively. Now we introduce a positive large parameter eta. Yesterday, Takei-san already introduced this letter eta as a large parameter, but I'd like to explain why we use eta as the large parameter. Historically, of course, it looks better to use h bar inverse instead of eta. We use x as the independent variable and y as the variable in the Borel plane. The Borel plane means the space of the variable of the Borel transforms with respect to the large parameter or its inverse. In the theory of partial differential equations, it is common to use x, y as the independent variables of the two-dimensional space and xi eta as their dual spaces, dual variables. So it is natural to consider eta as the symbol of the differential operator ddy, and hence as the large parameter. So this is why we use eta as a large parameter. And, we introduce the large parameter in the parameters of hypergeometric functions or confluent hypergeometric function. That is, we set A to be alpha naught plus alpha eta, and so on. That is, the parameters contained in those functions are a linear function of the large parameter. Then we have the Gauss equation of this form and Kummer equation of this form. A little bit messy, but we consider these equations. Then we can construct WKB solutions of these equations. We said phi plus minus bar phi or phi. And next we take the Borel sums of these formal solutions. And our problem is that find the constants C plus minus and C plus minus tilde for which this relation hold. So this is very naive and in a sense elementary question. So this is what I will show. I like to show you. Again, this is the hypergeometric series and the hypergeometric differential equation. The so-called Riemann scheme of this equation is given here. This means that the first row designates the regular singular points, that is 0, 1, and the infinity. And the second and the third row means the characteristic exponents at each regular singular points. And it is well known that there are 6 standard solutions of the hypergeometric equation. And each solution have 4 different expressions. And in total, there are 24 solutions that are called Kummer's 24 solutions. You can find the explicit form in BMP or those handbook. And any 2 of them forms a basis of the solution space. And the standard basis of the solutions space of hypergeometric differential equations are U1, U5, or U2, U6, or U3, U4. This corresponds to the regular singular points, the origin, 1, and the infinity. And also you can find in those formula handbook the classical connection formulas. For example, U1, U5 is written in terms of U2, U6 with coefficients given by gamma functions. And similarly, so classically, we know very well about the hypergeometric function. So as I said earlier, we introduced the large parameter eta in the parameters contained in the hypergeometric differential equation in this form. And we assume that the alpha, beta, gamma, that is the coefficient of eta in each parameters, alpha, beta, gamma does not belong to this exceptional set E1 union E2. Here, E1 is defined by this relation and E2. And this means that we consider the case where the Stokes geometry is non-degenerate. To apply the standard theory of the exact WKB analysis, we eliminate the first order term of the hypergeometric differential equation by setting this gauge transform that is W equals some power function times psi. Then we have an equation for psi in Schrödinger form. Here, Q has some complicated form, but we can compute in this form. And by the assumption, there are two simple turning points, tau plus minus, that is simple zeros of the leading term of the potential Q. Okay, this tau plus minus is a root of this quadratic equation. And then you can construct WKB solutions of this equation. Here, S is a logarithmic derivative of unknown, and S satisfies the Riccati type equation. As Takei told yesterday, S satisfies, S can be written in this form, and each coefficient Sj is determined by this recursive relations. The leading term satisfies this quadratic equation. So if you choose one of square root of Q naught, then higher order term Sj are determined uniquely and successively. Now, of course, there are two choices of branches. We take the branch of square root Q naught like this near the origin. And if you choose minus square root Q naught, then you have S minus. And according to this plus minus sign, you obtain two formal solutions of Riccati equation. And a Stokes curve emanating from a simple turning point, tau, is defined by this analytic equation. Next, we introduced S odd and S even. That is, S odd is half of difference of S plus and S minus, and S even is average of S plus and S minus. And if you put this S plus minus into the Riccati equation and compare the parity of the equation, you obtain this relation. That is, S even is minus 1/2 of logarithmic derivative of S odd. This means that you can take normalization of the integration of S even as minus 1/2 logarithmic of S odd. So we can take WKB solution normalized at the turning point tau in this by this equation. That is the square 1 over square root S odd comes from this normalization of integration of S odd, S even, and this part is understood as a half of contour integral starting from x and go around the simple turning point tau and going back to x. Anyway, this WKB solution is very important in our analysis. And going back to the original Gauss equation, we have the WKB solutions, phi plus minus of the Gauss equation. That is, this gauge transform recovers the first order term. To state our main results, we need the classification of Stokes geometry. We introduce 4 sets, omega 1, omega 2, omega 3, and omega 4. These sets are subset of open subset of the space of parameters alpha, beta, gamma. Omega 1 is given by this condition, and so on. And the next, we take a group G generated by involutions tau m, defined by this one. Those involutions are classical symmetry of hypergeometric equation. And next, we set capital pi k to be the union of images of omega k by this group. And the union of pi k is an open dense set, and the complement is our exceptional set. So almost all part of the parameter space are covered by the union of pi k. Now, the Stokes geometry of the Gauss equation is classified in terms of the number of Stokes curves flowing into the singular point. That is, star means 0, 1, infinity, or the infinity. That is the regular singular point of the Gauss equation. And N star denotes the number of Stokes curves flowing into the singular point star. And we set n hat the triple of n node n1 and n infinity. And our first theorem is if alpha, beta, gamma belongs to pi 1, then n hat is 2, 2, 2. This means that two Stokes curves emanating each singular point into each singular point. Our main result. Because we have a symmetry, it is sufficient to consider the case alpha, beta, gamma belongs to one of omega k for four cases. And for the sake of simplicity, we assume that alpha, beta, gamma are real. First case, if alpha, beta, gamma belongs to omega 1, that is alpha, beta, gamma satisfy this condition, then we take the turning point tau node as this one. Here we take the branch of square root as imaginary part is positive. You see that by this condition, this part is negative. So we take the imaginary part of this one is to be positive. This is tau node. And this picture is a typical example of the Stokes geometry of the Gauss equation. Tau node is this turning point, and tau 1 is another turning point. And there are three Stokes curves emanating from each turning point, and two of Stokes curves flowing into each regular singular point, 0, 1, and at the infinity. And let R1 denote this domain that is surrounded by four Stokes curves flowing into the origin and x equals 1. Okay, and let capital phi plus minus denote the Borel sum in that region R1 of the WKB solution phi plus minus normalized at the simple turning point tau node of the Gauss equation. Then the basis U1, U5, U1, U5 is given here, is expressed in terms of the Borel sum of WKB solutions as this in this form. Here, the coefficient C11, etc., is given in this form. Okay, this is the first case. And similarly, the second case, alpha, beta, gamma belongs to omega 2, this condition. Then you have Stokes geometry like this. And we take tau node here. And R1, you take R1 as this, this domain. Then we have such a relation. All the coefficients are explicitly written in terms of gamma function and exponential function. And the third case, Similarly, and the fourth case. Summing up, this is a handbook style descriptions. There are four cases: first, second, third, and fourth. And in each case, U1, this is U1, that is the classical hypergeometric function. And this is independent solution U5 are written in terms of the Borel sum of WKB solution, capital phi plus or capital phi minus. This is our main result for 2F1 case. The proof consists of 3 steps. That is, first step, we compare 2F1, that is classical hypergeometric function. Of course, alpha beta ABC contains the large parameter. We compare this one and the Borel sum of the recessive WKB solution normalized at the origin. And second step, relate 2 ways of normalization, namely normalization at the origin and at the simple turning point. And this step includes the definition and the computation of the Boros coefficients of the hypergeometric equation. And in the third step, we compute the Borel sums of the Boros coefficients, and also we compute the local monodromy matrix of the Borel sum of WKB solution around the origin, and comparing the matrix and the local monodromy matrix of classical basis U1, U5, then we have our relations. So this is first step. We take a WKB solution normalized at the origin. That is, we define psi plus minus node by this equation. That is, we exclude the pole part of SOD, and then we can integrate this one. Of course, this is formal, so formal one, formal power series. So this means term by term integration. And instead of excluding this term, we multiply the power function x to the power plus minus half of c minus 1. And this WKB solution is corresponding to classical hypergeometric function. If this one of this is recessive, that is recessive WKB solution by the choice of our branch of square root, phi plus node is a recessive solution, and This one is Borel summable near the origin. Precisely speaking, it is Borel summable outside the origin, and the origin is a removable singularity, and its Borel sum becomes a holomorphic solution of the hypergeometric differential equation. So there is some constant that is it is a constant multiple of the hypergeometric function, and the constant can be computed by evaluating at the origin, and we have such relation. And second step, we compare the two normalization. Normalized at the origin and normalized at the simple turning point. Formally, this is connected by such a exponential of this integral. And this integral is divided into two parts. And the first one is V naught. And this is called the Voros coefficients of our equation at the origin. And we need some additional term defined by this limit. Here, SO positive or SO negative are defined by this. That is, SO positive is a negative power part of SO with respect to eta. And SO negative means a positive part of the powers of eta. Then we can compute the explicit form of the Voros coefficient in this form. Here, Bn is a Bernoulli polynomial. An explicit form of the additional term, this one, this is somewhat messy, but we can compute this explicitly by looking carefully at the residue of S odd at each regular singular point. Of course, to compute these residues, we need to put a branch cut, and branch cut is given by wavy line. For example, if the parameters are contained in omega 1, we take this branch cut and so on. And the additional terms can be computed explicitly in these forms. And we skip the proof. And finally, we compute the Borel sum of the Voros coefficients for each parameter region. And combining the additional term, we obtain such expressions of the Borel sums. Summing up, we obtain the relation between the classical hypergeometric function and recessive WKB solution normalized at the turning point, simple turning point. And other relations are obtained by comparing local monodromy matrices at the origin with respect to U1, U5, and to phi plus, phi minus. Now, applications. By Watson's lemma, WKB solutions are WKB solution gives an asymptotic expansion formulas for its Borel sum when the large parameter tends to the infinity. So, for example, if alpha, beta, gamma belongs to omega 1, and U is the U locate in the neighborhood of the origin, then this classical hypergeometric function with a large parameter eta has an asymptotic expansion formula of this form as eta tends to the infinity. I examined numerically by using Mathematica, and I choose parameter like this, and plotted by Mathematica, and our leading term fits very well. So I hope this supports our formula. Of course, there are many works concerning asymptotic formulas of hypergeometric functions with respect to large parameters. For example, classically, Watson gave some asymptotic formula for hypergeometric function in this paper, and recently, Adri gave several formulas that gives uniform asymptotic expansions for hypergeometric functions. And most of these works treat the case where the parameter belongs to our exceptional set. On the other hand, we assume the parameter does not belong to the exceptional set. One of the advantages of using WKB solution is that we can apply connection formulas for WKB solutions. So applying the connection formulas for WKB solutions, we obtain asymptotic formulas for the basis for x far from the origin. Of course, but not as, but outside the Stokes curves. This is an example. If the parameter belongs to omega 4, this is a typical Stokes geometry. And we consider this R3, this region R3, for x in R3, we have such an asymptotic formula. Of course, eta tends to the infinity. This is obtained by using connection formulas of WKB solutions. The second application is the parametric Stokes phenomenon. Let phi plus 1 and capital phi plus 2 denote the Borel sums of for x in the region R1 for alpha, beta, gamma belongs to omega 1 and omega 2 respectively. Then we have such a formula. So this means that we can give not only asymptotic formulas for hypergeometric function as eta tends to the infinity, but also formulas describing parametric Stokes phenomena. Next, I will show you the similar formulas for the Kummer equation. We introduce the large parameter eta into the Kummer equation and obtain this equation. A standard basis of analytic solution space is given by the Kummer function and this one. Please note that the variable x times large parameter, we consider such a situation. Our assumption is the parameter alpha gamma does not belong to E1 defined by this one. Then the Stokes geometry is non-degenerate. And eliminate the first order term and construct WKB solution. Then similarly, we obtain the relation between 1F1, that is Kummer function, with the large parameter eta, and the WKB solution normalized at that simple turning point. Of course, similarly, computing local monodromy at the origin, we have another relation, that is independent solutions of Kummer equation can be also expressed in terms of the Borel sum of WKB solutions. So summary, and we have obtained the linear relations that hold between the hypergeometric function 2f1 and the Borel sums capital phi plus minus of the WKB solutions of the Gauss equation. Using the classical connection formulas, we can obtain the linear relation between the Kummer's 24 solutions and the Borel sums of the WKB solutions. We also have similar relations for the confluent hypergeometric function 1f1, and these relations are consistent with the procedure of the confluence from Gauss to Kummer. And these relations give asymptotic expansion formula for hypergeometric function and of the confluent hypergeometric function with respect to the large parameter for any x outside the Stokes curves. These are references. Thank you for your attention.
Thanks so much, Aoki-san. Thank you very much. So now the session is open for questions or comments. If you have questions, you can cut the mute and please ask the questions, give the comments.
Sorry, I have a question.
Sure, Go ahead.
So when you plot these Stokes regions, you have simple turning points, but then I've also noticed that at some points there's only one line that goes into the point. So what is the local behavior of that Q function? For a simple turning point, it's the local behavior, if you expand around that point, would be quadratic, right? But then you have these points where there's only one line going into them.
Sorry, you mean the case where one line emanates from
Yes.
That case we exclude. Our assumption, we assumed that the parameter does not belong to E1 union E2, and
Okay.
That condition assures that all the turning points are simple. So always there are 3 Stokes curves emanating from a simple turning point. Of course, it is interesting to consider the case where one Stokes curve emanating from a simple pole type turning point, and it should be investigated, but we have not yet.
Okay, thank you.
Okay.
Andrei Voros has written in the text that he very much enjoyed your talk. And he has a remark that the Binet formula is also essential in the resurgence analysis for the harmonic oscillator. And the question is this a coincidence?
Excuse me. Okay. Of course, to compute the Borel sum of the Borel's coefficient, we used the Binet formula, and the Borel's coefficient of the hypergeometric function has a form that is sorry. This is the expressed form of the Borel's coefficient of the hypergeometric function equation at the origin, and this is a sum of such terms, and each term is corresponding to the Borel's coefficient of the wave equation. So computing the Borel sum, we use the Binet formula. So similar computation works also in our cases.
Also a comment by Gergo. Do you want to state it, Gergo?
Okay. Hi, Takashi.
Hi, how are you?
Fine, thanks. It was just a comment on Daniel's question. So can you show me one of the Stokes graphs related to the Gauss hypergeometric function? Yes. So the thing is that the turning points are tau1 and tau0, and you can see that there are 3 Stokes curves emanating from those. But the other points are, I believe, called new transition points by Koike. So those are coming from singularities of the coefficient functions in the Schrödinger equation. So those are not turning points, but other types of transition points, poles. And the Stokes lines, some of the Stokes lines are running into those points.
I see. And do you understand why it is that the lines just, there's only one line going into that sort of singularity, or what the type of singularity is?
Are you at this point? The
It's
origin?
a simple pole, then there is only one always that emanates from it, right?
Okay.
Under our assumption, we only consider the simple turning point, and if under our assumption, the Stokes geometry is non-degenerate. That means there is no Stokes curves connecting turning points. This means that any Stokes curve flows into one of the singularity. So,
Right.
So how shall I say? Anyway, we don't consider the simple pole type turning point, and
sure.
This picture shows that the turning point emanating from tau naught flows into the origin. Origin is not a source of the Stokes curve.
Right. Okay, thank you.
Maybe I have a question, Professor Aoki. So is this part of a larger program that you have to sort of take, all of these very classical differential equations, which often have very standard sets of, or some of them at least have standard sets of preferred solutions, and to just compare them, kind of build this very large dictionary between those standard solutions and WKB solutions? Or did you have a specific interest in these two equations, for some different purpose?
What do you imagine? What equation do you imagine?
Well, I mean, of course, immediately comes, Gauss hypergeometric, of course, is a very classical. But then there are many others that you could consider which have kind of preferred at least locally defined bases of solutions. I mean, I'm thinking immediately like Bessel equations or Hoyne equations or things like that. So they all have kind of, you know, people have worked out for centuries now preferred bases of solutions. So I'm just wondering if this is kind of part of a larger program of comparing that, you know, or building a dictionary between those very classical solutions and what you get from WKB analysis.
Of course, it's a very interesting problem, and at least the confluent family of the Gauss hypergeometric equation, we have almost complete dictionary.
Right.
As far as the parameter satisfies some generic conditions.
Mm-hmm.
For example, the Bessel,
right.
Bessel is written in this form. This is done by my collaborators, and Shen and Silverstone gave the relation between the wave function and the WKB solutions. And this is classical, but ARA is explicitly written in terms of WKB solution in this form.
Yes, so actually Andrei Voros just wrote in the chat, kind of continuing my question, something I had in mind as well.
Matthew and Lame, of course, it is an interesting problem, but it is related to Hoyne's equation, and we have no result concerning Hoyne's equation. It is a very difficult problem. We hope to try to consider the Hoyne equation, but at the present, we find no way to approach the Hoyne equation by our method. One problem is, of course, the problem of accessory parameters. To derive the Boros coefficient, we essentially used ladder operators. But as far as I know, there is no ladder operators for Hoyne equations. So, and also how to treat the accessory parameters. It's a big problem. But for higher order case, we have some results for generalized hypergeometric differential equation. For example, we can compute the Boros coefficients for the equation of 3F2 at the origin and at the infinity. But at the regular singular point x equals 1, it's a big problem. We cannot compute the Boros coefficients for x equals 1 for 3F2. Anyway, some extensions for higher order case are also possible.
I see. Very interesting. Thank you very much.
Constant. So we have some more comments from Andre Pauls. Accessory parameter problem relates to constants, constant and downs uniformization mark problem. So maybe Zero is still here for event. I think
Yeah, it's a kind of highly degenerate version of Hoyne where you take all the singular points and coalesce them into the point infinity.
I think so.
May I ask another question? I guess maybe slightly more kind of a practical question. So if you're considering Gauss hypergeometric equation, your strategy is to first convert it to a Schrödinger equation by doing this gauge transformation. Is that a really necessary step in order to do the analysis, or is it really more of a convenience?
I think it's not necessary, but there is a good standard theory, so I prefer to apply it. That's all.
Right.
I guess part of this has been discussed, but is there any other, do you see like obvious generalizations of these connection formulas and asymptotics that you find to other problems, and apart from the ones that Nikita has mentioned as well and have been discussed?
I'm sorry?
Other generalizations that you could also obtain asymptotic formulas for beyond the hypergeometric functions.
Generalization to what?
Other special functions, meaning different types of special functions. Do you think that the same type of calculations could work? I'm not sure if the question makes sense. I'm just asking just
of course, our theory is limited to the confluent family of hypergeometric functions. And as I said earlier, if the number of singular points is greater than 4, this means Hoying function or more general equation, we have no strategy to approach such equations. So our result is very limited to classical special function.
May I ask regarding regarding the confluence procedure itself and kind of using WKB for the global analysis of a differential equation. So normally this is a very difficult problem that let's say you have a differential equation with an irregular singularity, and you want to understand Stokes data, let's say, of the irregular singularity. And one way you could try to approach this is to kind of do a deformation on your differential equation where you split the irregular singular point into several simple poles. And then you describe the monodromy around each simple pole. And then you try to understand how the monodromy, as you coalesce these simple poles into your original irregular singular point, how these monodromies assemble into Stokes data. So in general, this is a very, I mean, it's a very attractive idea, but apparently it's extremely difficult to actually make this work. I wonder if you can see whether this problem is somehow made easier or is more accessible if you apply techniques of the WKB analysis, using WKB solutions. Do you have any comment regarding that?
I don't know well, but classically, Ramis wrote a paper that treat confluence, the relation between monodromy matrix and the Stokes matrix between hypergeometric equation and the Kummer equation. So some kind of such consideration can be possible, even for classical objects. So also, I guess some discussion can be possible for by using WKB.
But you wouldn't necessarily say that these techniques somehow lend more clarity to this confluence of monodromy data problem, or is it that you simply haven't considered this yet?
At least to compute the monodromy matrices, WKB analysis is very powerful. So
of course,
even for the case the monodromy matrices is not known by classical analysis, we can compute it if the Stokes geometry is not degenerate. So you may have some discussion about such problem.
Yes. Okay.
We still have time, but so if there are questions or comments, some more questions or comments?
Yeah, may I ask one question?
Sure, go ahead.
Yeah. Aoki, you have established an exact relationship between hypergeometric functions and the Borel sum of WKB solutions. Then, by using this relation, can you say something about the relationship between the integral representations? More precisely, between the integral representation of hypergeometric functions and the Borel sum of WKB solutions. Can you say something about these two, the relationship between these two objects?
I have no idea. I hope there is some relation. I want to find it, but now I don't have any idea.
But anyway, your relationship is truly exact. So I believe you can say something about these two integrals.
I hope so.
Yeah. Okay. Thank you.
Perhaps we could also go to the non-recorded.
Yeah, maybe.
So I will stop the recording.
Ask questions.
So, well, again, thank you so much, Professor Aoki, for the talk, and I will now stop the recording and start the, any possible questions that will not be recorded.
Stupid questions are also okay.